Hello viewers, in today's lecture we are going to discuss two very important problems from homogeneous differential equations, right? So in this session we are going to solve these two important differential equations which are homogeneous differential equations, right? And we'll also see that how we can convert or prove that these two differential equations belongs to the set of homogeneous differential equations, right? So let us start. So now here what we will do, will again first of all rearrange the terms. So we have xy dx is equal to x square plus 2y square dy, right? Now let us form an expression in terms of dx over dy. So taking dy to the denominator of dx, we have dx over dy is equal to x square plus 2y square over xy, right? So here we have an equation where we have dx over dy, right? And in the first case we have seen that we had the equation dy over dx, right? So whenever we come across with this type of differential equation where we have dx over dy, then we'll solve this type of homogeneous differential equation by taking taking the substitution x over y is equal to v, where v is some function of y, right? So we can write x is equal to vy. So here let us take this function as f of x comma y, and let us see whether this function is homogeneous or not. So what we will do, will replace x by lambda x and y by lambda y. So here f of x comma y can be written as x square is lambda square x square, then we have 2 times lambda square y square, and here we have lambda x times lambda y. So we can take lambda square common in the numerator. We have x square plus 2y square. Here we have lambda square xy. So lambda square get cancelled. So we are left with, here we can write f of lambda x comma lambda y, right? So f of lambda x comma lambda y is equal to x square plus 2y square over xy, which is our original function f of x comma y, right? So it means this function is independent of lambda, right? So we can also write it here lambda raised to 0, because lambda raised to 0 is equal to 1. So whenever we express a function f of x comma y like this, then the function is said to be homogeneous, right? So now let us come to this function f of xy. So we can now express f of xy as x square plus 2y square over xy, dividing the numerator and denominator by y square. We have x square over y square. Here y square get cancelled, and here we have simply x over y, right? So now we can write x square over y square as x over y square, and here we have plus 2, and here we have x over y, right? So now we can see that this dx over dy, which is equal to this function, which is f of xy, is equal to this function, that is x over y square plus 2 over x over y. Now this function is of the form that is phi of x over y. So whenever we have an expression like this, then we can solve the differential equation by taking x over y. X over y is equal to v where v is a function of y, then x is equal to vy. So differentiating both sides, we have dx over dy is equal to, here we'll apply the product rule. So we have v times 1, the derivative of y with respect to y is 1, then we have y times dv over dy, right? So we have dx over dy is equal to v plus y dv over dy, right? So now we can replace this dx over dy by v plus y dv over dy, and here we have x over y as v, so we have v square plus 2 over v, because x over y is v. So now we have to solve this differential equation, which is now in terms of v and y. So now let us take this v to this side. We have y dv over dy is equal to v square plus 2 over v minus v, and now v times v is v square, so we have v square plus 2 minus v square over v, and v square and minus v square get cancelled, so we are left with 2 over v. So we have y dv over dy is equal to 2 over v, and now this is a variable separable form, right? So we can separate the v's and y's. So we can take v to the left hand side. We have v dv, and here we can write 2 dy over y. Now integrating both sides, here we have c as the constant of integration. So the integral v dv is simply v square over 2, because here v raised to 1, and we have v square over 2. Here we have 2 times log of y, because the integral dy over y is log y, and c is the constant of integration. Now multiplying throughout by 2, this equation, we have simply v square. Here we have 4 times log of y, and here we have 2c. Now let us replace this v by x over y. So now we have here x square over y square is equal to 4 times log of y plus c. So here we can take this constant of integration as a c prime, so that we can replace c prime by 2c, right? So c was our constant of integration, so is 2c, and 2c can be replaced by some other constant, that is c prime, right? So this is the general solution of this differential equation. Now we have to find out the value of this constant of integration c prime by taking the initial conditions or the boundary conditions. So we have y of 0 is equal to e. So this is the value of x. So x is 0 when y is e, right? E is the exponential number. So substituting these values in this equation, we have here 0 square over e square. Here we have 4 times log of e, and here we have c prime, right? So this term is 0, so here we have 4 times 1, because log of e is equal to 1. So here we have c prime. So now c prime is equal to minus 4. So the constant of integration is equal to minus 4. So substituting this value in this equation, we have x square over y square is equal to 4 times log of y minus 4 is the particular solution of this differential equation. We can also express this solution as x square over y square. Here taking 4 common, we have log of y minus 1, right? And 1 can be replaced by a log of e, so we have log of y minus log of e, because log of e is equal to 1, right? So we have x square over y square is equal to 4 times log of y over e, because here we have the property of log, that is log of m minus log of n is equal to log of m over n, right? So this is the uh, another form of the particular solution of this differential equation when the conditions are y of 0 is equal to e.